There's for USC School of Medicine here, Keck School of Medicine. There's going to be a talk by the Assistant Dean of Admissions. So I'll post this on Canvas if you're interested. This is tomorrow at 5 to 6:30 p.m. And then on Saturday, there's a Space Science Day. If you're interested in volunteering for this, I have some flyers here. There's no advanced sign up, you just show up. Okay, any questions? Get started? No. How did the test go? Okay. All right. Well, today we're just going to continue with chapter 17. So let's do that. And then I was thinking, I scanned the multiple choice portion of the test. I can hand that back, but the free response I haven't finished grading yet. So if you want, I'll give those back to you today. You can see. All right, so we're continuing with acids, and we were looking at HCN last time. And so we would just follow the same process. We have HCN. You know, for acid solutions, this is our strategy. Our strategy is we look for hydronium ion producers. In an HCN solution, there are two hydronium ion producers. What are they? Well, one is the acid, and the other is water. But does water produce much hydronium? No, it doesn't. And so sometimes, if we're only interested in pH, sometimes we can ignore the water because it's such a negligible contributor. But other times we can't ignore the water because it's a significant contributor. So the last two problems we did, one where it was a negligible contributor, 6 molar HCl, and the other was where it was a significant contributor, which was 10 to the minus 8 molar HCl. And so here we have HCN, and the initial molarity here, when we look at hydronium ion producers, we start off with the largest, which will be HCN, and I gave it, 1.00 times 10 to the minus 7 molar, is that where we left off? I think so. Well, one thing is that's very low concentration. It has a very low concentration, but HCN is still a very poisonous acid, so we have to be very careful with that. It's hydrocyanic acid. Hydrogen cyanide gas was used in the gas chamber at San Quentin prison. They'd make it, though. You know how you make hydrogen cyanide gas? How you make hydrogen cyanide gas is you take a cyanide salt, like sodium cyanide, and add acid. When you add acid, then you're going to have an acid-base reaction or metathesis reaction, and it can generate hydrogen cyanide gas. So it could be produced on demand rather than keeping a container of that, which is much more dangerous. But acid plus water makes hydronium and the conjugate base, cyanide. And so this is what we call our Ka equation. Ka equation is going to be hydronium times cyanide divided by the HCN. Now, HCN isn't one of the strong acids that we memorize, and so we would consider it a weak acid. And a weak acid, what's the Ka value? Did someone write it down? The Ka value? I looked it up in Appendix D. 6.0 times 10 to the negative 10. 10 to the negative 10 tells me it's a very weak acid. You know, why? Because we form so little hydronium. We'd expect very little. This is going to be heavily biased towards the molecules. So the molecules don't like to break apart. But what we're going to do is, we're going to imagine none of them have broken apart. And so this is resetting this, to all molecules. So we have 100% molecules. But we know some of them will break apart because, you know, it's 10 to the minus 10. A small fraction will break apart. And so the change here is going to be minus x molar, and then water is pure liquid. This will be plus x molar, and then plus x molar here. And so at equilibrium, we're going to have 1.00 times 10 to the minus 7 minus x molar, and then x molar here, x molar here. Now, you know, I already mentally did this, but I could start off with these initial conditions and get this ice table, or I could reset the initial conditions. Should I start off with these initial conditions and use this ice table, or reset this and generate a different ice table? Leave as is, yeah. We leave it as is because this is going to have the smallest change. If I reset this, then I'd have a big change. And when you have a big change, then it causes problems with your calculator. And so this is going to be x times x, which is going to be x squared divided by 1.00 times 10 to the minus 7 minus x. The other reason we want a small change is what? The other reason we want a small change is because then the simplifying assumption is more likely to work. If it were a big change, the simplifying assumption would for sure fail. And so in this case, I'm going to say that x is much smaller than 1.00 times 10 to the minus 7. And therefore, x squared divided by 1.00 times 10 to the minus 7 minus x is just going to be x squared divided by 1.00 times 10 to the minus 7. Because the x we're assuming is negligible compared to the initial. That may or may not be the case. And so this is going to be x. We can just solve this, I think. Is going to be 6 times 10 to the negative 17, square root of 6 times 10 to the negative 17, which we'll just do in the calculator here. Skipping some steps. And I get 7.745. 7.745. I usually carry all extra digits, but I'm not going to carry all of them. They're just too many digits to carry. Maybe up to 9, 459. Should be good. Times 10 to the 3, 6, 9, times 10 to the minus 9. Okay. Oh, shoot. I forgot to add pages to this. Let me go ahead and save this. All right, then we're going to calculate the percent change. The percent change is going to be the change. In this case, the change is just x divided by the initial. I'm just going to write initial here since I don't want to write that over again, times 100%. And so that's going to be 7 divided by 1 times 10 to the negative 7. Times 100. And I get a 7.745%. I don't need to be that precise. But I get a 7.7% change. A 7.7% change means the essay failed. So I'm going to use it. So that means what we're going to do instead is we're just going to use the quadratic equation for this. And so we'll need to get it into quadratic form. I'll save some room here so we can write the equilibrium concentrations. But getting this into quadratic form, I'll just do this kind of in my head a little bit. The danger is that I make a mistake. And so this is going to be x squared plus 6.0 times 10 to the minus 10x. Okay, and then this will be 10 to the minus 17. Will be minus 6.0 times 10 to the negative 17 is equal to 0. All right. In chapter 17 and 18, quadratic equations are very common. So if you don't have the calculator, it might be worth, spending $20 for it to save yourself. Well, actually, it would just be for the test, because you could just use a quadratic solver here. We'll do. One of these values here. So A was 1, B is 6 times 10 to the negative 10. C is 6, or minus 6, negative 6 times 10 to the negative 17. So let's go ahead and calculate it. And I have 2. The negative won't work here, so I'll just take the positive, which is going to be 7.45, 177 times 10 to the minus 9. So let me write that here. Oops. X is equal to 7.45177 times 10 to the negative 9. When we use the simplifying assumption, it came close. We got 7.7. Over here, we get about 7.45 or 7.5. So, but you can see at this, there's already a significant percent difference here. All right, so let's go ahead and calculate it. And so 1 times 10 to the minus 7 minus 7.45. Okay, so what I'm going to do is I'm going to minus 1 times 10 to the negative 7 here. Oops, no, I didn't quite get that. Do this calculation. So it's 1 times 10 to the negative 7 minus 7.45177 times 10 to the negative 9. And I get 3, 6, 7, 8, 9.25. Carry some extra digits. 9.2548. That should be enough to minimize round-off error. 9.2548 times 10 to the minus 8 molar. This is more sig figs than I'm allowed, but again, I like to carry that. And then x is 7.45177 times 10 to the minus 9. And this is the same here. So what we're going to do next is we're going to check our equilibrium concentrations and make sure that they work out to K. And so we'll check K here. Actually, I'm just going to punch it in my calculator. I don't want to rewrite these numbers here. And so I'm going to invert this times 7.45177 times 10 to the minus 9 squared. Let's square the whole thing. Let's see. Maybe not. Let's just try it. I guess it did work. So I check my K value and I get 5.99. How many nines do I have? 5 nines. And then a 3 times 10 to the minus 10. 10. Yeah. And so when I look at it, it should be 6.0 times 10 to the minus 10. We have 5.999993 times 10 to the minus 10. So it's good. This is just round off error. And so it checks. Okay. All right. So these would be our equilibrium concentrations. Since I'm not quite done, I'm just going to go ahead and write it here. 7.45177 times 10 to the minus 9 molar. There. All right. Now we ask ourselves, do you think water will be a significant contributor or an insignificant contributor to hydronium in this case? Insignificant? How come, would you say? Is it water? Well, we have to take a look at the hydronium we have here. And the amount of hydronium we have here is 10 to the minus 9. And water impure water can contribute up to 10 to the minus 7 molar. If we have common ion, this is called common ion, hydronium, there to begin with, it's going to be a lot less. But even if it's a lot less, the amount of hydronium we have here is so small that I worry about water. I would worry about water. Yeah. These are things, why am I talking about this? I'm talking about this for shortcuts. You know, we could take the long way and do all the calculations, but if you're only interested in pH, you might stop here. You might stop here if you don't think water is going to add much, and then you could save yourself a minute or a couple of minutes. On a test, it could be critical. You know? But we're going to worry about water. I mean, 10 to the minus 9, you better worry about it. And so I'm going to call this step 1 here. And then step 2, we'll look at how much additional hydronium we get from water. And we aren't going to get the full amount, 10 to the minus 7. A lot of people will say, we're going to get 10 to the minus 7. 10 to the minus 7 molar only occurs if there's no common ion. And the reason is we have to worry about Kw. Kw is going to be hydronium times hydroxide divided by the activity of water. Activity of water is just 0. I mean, not 0, 1, sorry. And so the situation with water is this. We start off with some hydronium there. If this were 0 and 0, then we get 10 to the minus 7, 10 to the minus 7. But since we have hydronium there, and, you know, Kw has to equal the constant, 1.0 times 10 to the minus 14 at 25 degrees C. We worry about that. And so what we're going to do is we're going to carry down this hydronium here. All the hydronium produced in step 1 needs to move down into step 2. So we're going to use that here. And so this is going to be the initial from HCl. And so this is going to be 7.45177 times 10 to the minus 9 molar. And then the hydroxide, we're going to reset the water. You know, pure water is pH 7, but we're going to say that we're going to reset it so that none of the water molecules have collided. And by resetting it, we're going to just call it 0. So we have no hydronium and no hydroxide from water yet. And so, you know, there's always hydronium and hydroxide, but what we're going to do is we're just going to imagine nothing's happened yet. And now what we're going to do is we're going to allow the water molecules to collide. And when they collide, they're going to produce some hydronium and some hydroxide. And they produce it in a 1-to-1 mole ratio. So I'm going to get plus X molar hydronium plus X molar hydroxide. But the amount I'm going to have is going to be a lot less than 10 to the minus 7 because now I have some to begin with. Here, 10 to the minus 9. It's supposed to be at 9. There. So I don't have to produce as much. And so what I'm going to have is I'm going to have 7.45177 times 10 to the minus 9 plus X molar times X molar. So I don't have to produce as much because I have that common ion there to begin with, or common species, 7.45177 times 10 to the minus 9 plus X times X. I didn't reset this. I didn't bother resetting this because, number one, I mean, it's already 0 here. I already reset it. I already reset it in my mind. You know, so I did a reset steps, just assuming that no water has collided yet. Otherwise, I'd have to do this via Le Chatelier's. If I didn't reset this, then, and this is what we did earlier, is I'd have an initial of 10 to the minus 7 and 10 to the minus 7 from water. And then that would be the initial hydronium from water, 10 to the minus 7, 10 to the minus 7. Then we perturb that equilibrium. We perturb that equilibrium by adding this much more hydronium. And so my new initial would be 10 to the minus 7 plus this, and 10 to the minus 7 here. Well, it turns out the algebra for that is more difficult to solve because I have 2 binomials rather than just 1 binomial here. So I automatically reset this even before starting the problem. I just assume that nothing's reacted. Yeah, and that's what we automatically do for all these acid problems, is we reset it, including the HCl. I mean, here, this is already reset, the HCN. I mean, at equilibrium, the HCN is going to have hydronium and cyanide. We just didn't know how much. So we just reset this and start over again. Do you see how that works? All right, and so we can try the simplifying assumption. There's a rule in our book. The rule is the simplifying assumption, the success of the simplifying assumption is going to depend on K. You know, the smaller the K, the better. And it's going to depend on the initial. The bigger the initial, the better. And so what people do is they take the initial over K ratio. If the initial over K ratio is greater than 1,000, then the simplifying assumption is likely to work. You know, but where exactly is that cutoff? So I never calculate the ratio. I think for me, I'll just go ahead and try it and see what happens rather than calculating the ratio, because the ratio is a gray area. I mean, if it comes close to 1,000, what do you do or whatnot? So I just go ahead and use it. In this case, we're just going to say x is smaller than 10 to the minus 9. X is going to be smaller than 7 times 10 to the minus 9. So if that's the case, then this is just going to be 7.45177 times 10 to the minus 9. And then the x disappears from the binomial, but we still have this x out here that doesn't disappear. And so the calculation is so quick. It's 1 times 10 to the minus 14 divided by 7.45177 times 10 to the minus 9. And so this is going to give me an x of 1.34 196 times 10 to the minus 6. And then we calculate the percent change. Can you already see that the percent change is going to be big? Percent change is 10 to the minus 6, which is the change over the initial 10 to the minus 9. The change is bigger than the initial times 100. So this is going to be about, 10 to the third times 100 is 10 to the fifth, 100,000% change. And so this is a fail. All right, so what I'm going to do is just the quadratic again. So we'll get this into quadratic form. So getting this into quadratic form, it's going to be x squared plus 7.45177 times 10 to the minus 9x minus 1.0 times 10 to the minus 14 is equal to 0. Okay, then we're going to go to the quadratic solver here. And so I'm going to put here 7.45177 times 10 to the minus 9. And then this one I'll put in negative 1 times 10 to the negative 14. Okay, and then calculate that. All right, so we get an x equals 9.63 435 times 10 to the minus 8. So this one I'm going to actually write out here. This is equal to 7.45117 times 10 to the minus 9. And then I'm going to make this times 10 to the minus 9 so I can add them. So if I make the exponential term smaller, 10 to the minus 9 smaller than 10 to the minus 8, then I have to make the coefficient term bigger. So I'm going to make the exponential term 1 smaller, 10 to the minus 9. And then I'll make the coefficient 1 bigger, 96.3435. Where did most of the hydronium come from in this solution? Well, if you look at the HCN produced 7.45 times 10 to the minus 9 molar hydronium, but the water produced 96. Almost 100 times, well, 10 times, almost over 10 times more hydronium came from water. And so what does this come out to? Actually, I'm going to punch this in my calculator. 7.45177, or 117 plus 96.3435. 103. .7946 times 10 to the minus 9 molar hydronium. So the total hydronium, which is the hydronium from step 1 plus the hydronium from step 2, is 103 times 10 to the minus 9. And then the hydroxide, which we're going to get very little of, is going to be 9.63435. 9.63435 times 10 to the minus 8. Actually, it's not a huge difference. And so what I'm going to do is I'm just going to double check the equilibrium concentrations by plugging that back into K here. Take this times this. See what we get. Times 9.63435 times 10 to the minus 8. All right, and I end up with this. I end up with, I'm going to move the decimal over. I end up with 0.999994 times 10 to the minus 14. Which is, 1, basically 1.0 times 10 to the minus 14. So this is good. This is good. For step 2, this is good. Do you see that? It works. But this is bad. This is bad for step 1. Why is this bad for step 1? Good for step 2, bad for step 1. So let me write that here. This is good. I said good for step 2, bad for step 1. And so why do I say that here? The reason I say that is, okay, step 2 is in balance, you can say, with these concentrations here. But if I go back to step 1, remember I checked step 1 and I said, okay, this is good because, 5.99999 is close enough to 6.0, right? In fact, they round to 6.0, it's no problem. So they're the same. But when I check my K, look at the concentration I had for the hydronium. But the problem is both of these are in the same container. And so all of a sudden I went from 7 to 100, over 100. So if I go from 7 to over 100, that's going to change it. In other words, what happens is this. If step 1 was in equilibrium, and it was in equilibrium, these are the equilibrium concentrations, and works out quite nicely, these equilibrium concentrations here. So step 1 was in equilibrium with these concentrations. I've just perturbed it by step 2. Is here I have 7.45, and then in step 2, I'll take my 7.45 and add another 96, so I get 103. 103, if I plug in 103 here, will this still be at equilibrium? So if I change this from 7.45 to 103, is my K still going to check? No. And so in other words, this is Le Chatelier's principle. Le Chatelier's principle says If you take a system at equilibrium, which step 1 was, and then you add additional hydronium, which way is it going to shift? It's going to shift to the left. Okay, so that's no problem. What we do is we go ahead and shift this to the left and then recalculate it. We could just do that, or we could reset it, and recalculate it, or we could just do a Le Chatelier's shift with the new initial conditions and then figure out what the new equilibrium conditions are going to be. But can you tell what's going to happen there? There's going to be a shift left. We're going to reduce this, bring it back into balance. But what's that going to do to step 2? Well, if we shift step 1 to the left, then that means that the hydronium goes down here, and then therefore this one should shift right. Okay, that's okay. So what we'll do is we'll fix step 1 and then go back to step 2 and fix step 2. But when we fix step 2, what's that going to do to step 1? It's going to perturb step 1. And do you see we're going to be going in circles? How can we get out of this? It's like those ants that just go in circles. Have you seen that? Until they die. Unfortunately, I hope you don't keep going in circles until you die, because it'll take you forever to get nowhere, right? And it's true. You'll get nowhere. We're in an endless loop. And so we're like those ants, or Sisyphus, or somebody else, We're in this endless loop. So how do we escape out of this endless loop? We reset it, and the same thing's going to happen. It's going to perturb the previous step. So these are 2 steps. Why didn't this happen before? Why this didn't happen before is because step 1, if you go back to HCl, both the HCl calculations we did were where HCl went 100%. It can't be perturbed. So this is the situation. It didn't happen before because K is very large. And so it doesn't matter if you add more product. If you add more product, it doesn't perturb it. And so HCl is very unusual, as all the strong acids are. The strong acids are not going to be subject to this. So if we could add more chloride to HCl, it's not going to shift it to the left, or any of these others. This because K is very large. It's one way. But in this case, HCN is a weak acid, and weak acids are going to adhere to this equilibrium here. So the point of this is that we're in an endless loop. And we'd be like the ants, and the ants would just keep going in a circle until they all die, because that's the path they're on. But we need to escape this path. And how can we escape this path?
Can we combine the equations?
Yeah, well, we have to do something, and so let me talk about that. We aren't actually going to combine the equations, but that's one of the techniques that could be used. So let me back up a step and talk about multiple equilibria. This is early. There's one weird thing about Microsoft Word. I've allocated the maximum memory usage to Microsoft Word, but there's still some limit where it says I run out of memory. And so Windows has changed. It used to work quite well where you could allocate lots of memory to individual programs and prioritize it. I prioritize this as number one. Something's weird. All right, multiple equilibria. How we solve this is we solve this using simultaneous. Method. Actually, we have two different types of multiple equilibria. Actually, let me write that in here. Here. We have multiple equilibria with no common species. If the multiple equilibria have no common species, and they're in the same container, then we can solve them independently. Solve independently. And so we just treat each equilibrium as a separate problem. Solve independently. However, if there is a common species with common species, we can't do that. With common species, we have to solve the multiple equilibria simultaneously, such that the common species will have the same concentration at the end. Such that, and so we don't do it in steps. Common species has same concentration at the end, or equilibrium, for both. The simultaneous method is difficult. And so this is difficult. Therefore, some easier versions have been, or tricks have been done to simplify it. The most common trick is we do a stepwise solution. Stepwise works only, it doesn't work all the time. It works only if successive steps do not perturb prior steps. Perturb means perturb significantly, you know. It's going to perturb, but if the perturbation's insignificant, that we can ignore it, it's like a drop. You know, a drop of water, if you add a drop of water to the ocean, the volume did change, right? But did the volume of the ocean change significantly? No. And so that's what I mean by perturb. Yeah, we're going to perturb it, but the perturbation is so insignificant, we'll ignore it. And so stepwise is the most common trick to avoid simultaneous. The two previous problems that we did with HCl were stepwise. And if you go back and look, step 2 does not perturb step 1 significantly. However, this is the first one where stepwise failed. The other approach is combined, but combined only works under very specific scenarios where you just combine the equations. Combine requires you to ignore some species in the equilibrium. But we're going to look at combined later. Combined doesn't work for anything we've encountered so far. Works for very limited number of problems. Chapter 19. In chapter 19. So what happened in this last problem was the stepwise failed. For 1 times 10 to the minus 7 molar HCN, stepwise failed. The stepwise trick failed. Therefore, we must solve simultaneously. There are 2 methods for simultaneous that we can try to use. The first one is just normal ice and system of equations. The second method is ice and mass and charge balance in system of equations. All we're trying to do is we have multiple unknowns, and we're just going to try to figure it out. And so what we'll do is we'll take a look at this one here first and see how we're going to do it. The way we are going to do it is we're going to write out the equilibrium here. And both of these equilibrium are occurring simultaneously. So one doesn't occur first and the other occurs second. Both of these are occurring at the same time. But the contribution, so the way we're going to figure this one out is like this. So the initial concentration of HCN, we have that here. Plug that in. And the initial concentration of hydronium, I'm going to put this as this. What we're going to do is we're going to assume none of the HCN has reacted. And so what I'm going to do is I'm going to reset this so that HCN hasn't reacted. And what that means is the hydronium in here is all going to be from water. And then we're going to have 0 from cyanide. Okay, there's going to be a change. We're going to call this minus X molar plus X molar plus X molar. And so that equilibrium, I'm going to have my HCN, which is initial, minus X molar, and water is pure liquid. And then I'm going to have my H3O plus from the H2O plus X molar here, and then I'm going to have X molar here. Now, when I go to water, I'm going to do a similar thing. For water, what I'm going to do is I'm going to reset this so that no water has hydrolyzed yet. And therefore, the hydronium in there came from H2O is pure liquid, so I'll ignore that. The hydronium in here is going to come from the HCN. The hydronium from HCN is what we call what? It's what we call X, right? X is the hydronium that we generate from the HCN hydrolysis. And so this is equal to X. And then the hydroxide, I'm going to assume that water has not hydrolyzed at all yet. So I'm resetting this as well with respect to water. And so the change here is going to be plus. Now I don't want to use X here because do you see I already used X? X is the hydronium from the HCN. So I'm going to call this Y plus Y plus Y molar. And so at equilibrium, I'm going to have this. I'm going to have the hydronium from the HCN plus Y. Y is going to be the hydronium from the water. And then I'm going to have Y molar hydroxide. And so now, well, I see that the hydronium from water is Y, so I'm just going to call this one Y here. That's my Y here. And so when I look at the equilibrium conditions for hydronium here, I'm going to simplify this into Y plus X here. And then when I look at the hydronium in the water, I'm going to have X plus Y. So do you see what's happening here is I'm solving these simultaneously for the same hydronium concentration at equilibrium. Because we know that, you know, X plus Y is the same thing as Y plus X. So X plus Y is the same thing as Y plus X. And so they have the same hydronium. And so in other words, these two equilibria simultaneously will have the same hydronium ion concentration at equilibrium. Well, if we have two unknowns, how many equations do we need? We need two equations. Right? So if we go to the first equation here, this is Ka for HCN. This is going to equal the hydronium ion concentration, which is going to be Y plus X, times the cyanide concentration, which is going to be X, divided by the HCN initial concentration minus X. And then if I look at Kw down here, I'm going to get X plus Y times Y is equal, okay, this is equal to 6.0 times 10 to the minus 10. This is equal to 1.0 times 10 to the minus 14. All right, and then solve for X or Y, you know. This looks simple, right? Two equations, two unknowns. Does it look simple to you? Try it. Try at home. You know, there's some things you don't want to try at home. This is one you want to try at home, but I don't know. I'm not good at math, you know. So it's not so easy. But maybe if it's easy, if you're good at math, maybe this is easy. But you'll realize, like, if you're bad at math, or not so great at math like me, then it's going to be very, very challenging to solve this. But try it and see if you can solve it. Because to solve this, you can't, it's not straightforward, so you end up having to use tricks in order to solve this. Do you know that? It's not like a straight, okay, solve for y and then get x, because this is going to be x squared plus y. And over here we're going to get x plus y squared, xy plus y squared. So now you got to factor out the x, or you got to factor out the y. How are you going to do that? So in other words, this is not straightforward. You have to use tricks in order to do this. And so for Chem 1B, if we run into a scenario where it's simultaneous, then you would basically get 100% for setting it up like this, and recognizing that it's simultaneous. Okay, you can solve this for bonus credit. Lots of people do. I mean, it's not impossible. For some people, it's totally reasonable to solve this. This would be bonus credit. And then we figure out what the y plus x is. I'm not going to spend a lot of class time talking because it's algebra. You know, although I'll post the solution. I'm going to post the solution for mass and charge balance. Mass and charge balance is used commonly to solve lots of problems in this. This is a very common method to solve difficult problems. I'm going to post this on Canvas. If you're interested. It just is kind of time consuming. So if I gave one of these problems on the test where you actually solve for x and y, it takes some time. Some people are very fast at this, so some people can manage it. Once you do one, then it's not so bad. The book goes through it. The book will give you some hints about how to solve this, what types of tricks you need to solve this. So take a look at this section in the book. All right, so whenever we have simultaneous equilibria, what we try to do is we try to avoid simultaneous equilibria. We try to avoid simultaneous equilibria because it's difficult. And so instead what we try to do is we try to the stepwise trick. Hopefully the stepwise trick works. Because if the stepwise trick works, then it's a lot easier. The stepwise trick works for most of them. Most of the problems that we're going to do stepwise works. A few of them, it doesn't. We have to go full simultaneous. And the combined fails for all these in these chapters, chapters 16, 17, 18. 16, 17, 18, combined method fails for everything, except in chapter 19, we'll have some very unique scenarios where it works. So is this clear? Whenever we have multiple equilibria, we have to use the simultaneous method, but we don't want to use the simultaneous method. Whenever we have a gas, we have to use the van der Waals equation, but we don't want to have to use the van der Waals equation for every single gas. We'd like to simplify it by using the trick of the ideal gas law and then and then call every gas ideal. Whenever we use K, we should be using activities, but we don't want to use activities, so we're going to use a trick of just estimating that the stoichiometric concentration's close enough to the effective concentration. But do those tricks always work? No, and the tricks don't always work, and so when they fail, you got to know what to do. For us, if the concentrations fail, what we do is we just say, oh, there's going to be a big error in our calculation. We'll just live with it. All right, any questions on this? Okay, I'm getting,
Is the quiz on Monday?
for what?
Chapter 17.
No. Oh, the quiz or the exam?
Either.
Quiz maybe, but not the exam. Chapter 17, I still need to get through some more
Oh.
of this. Let's look at some polyprotic acids. Polyprotic acids, what we want to look at for are all hydronium producers. Actually, maybe I need to talk about one more thing before I go to polyprotic acids. Let me talk about acid-base conjugate pairs. Sorry, acid-base conjugate pairs. When we go to Appendix D, let's see. Or actually, I'm not going to go to Appendix D. We don't have that much time. If we go to the chart there, do you see that chart? It says relative strength of acids and bases in aqueous solution. But all I see are the strengths of the acids, Ka. Do you see that? Ka. Where's my bases? Where are my bases? Well, the bases and the base strength are going to be related by the conjugate relationship here. And so what I have for bases is I have Kb. And so this is base plus water, hydrolysis, Kb. And so ammonia has a Kb value of 1.8 times 10 to the minus 5. And so the Kb equation looks like this. It's the base plus water. And what does that yield? Base plus water yields, in this case, it's going to yield ammonium plus hydroxide. And that's Kb. And so Kb is going to be the ammonium concentration times the hydroxide concentration divided by the ammonia concentration. Now, interesting thing happens. Where did I get this number, 1.8 times 10 to the minus 5? Is it on that chart there? It's not on the chart. So is there another chart that's missing in this room? And it turns out there's no other chart that's missing in the room. Because the Kb for ammonium is equal to this. So Kb for ammonium interestingly enough, Kb for ammonium times the Ka, oops, what am I saying? Ammonia. Kb for ammonia, ammonium's an acid. So Kb for ammonia times the Ka for ammonium, this is what I was thinking, ammonium, is equal to Kw. And so the Kb for ammonium, ammonia is ammonium times hydroxide divided by ammonia. And the Ka for ammonium is the hydronium times ammonia divided by ammonium. So if we multiply these two together, everything cancels out except for hydronium and hydroxide. So the ammonium cancels out, the ammonia cancels out, and we get hydronium and hydroxide, which is Kw. And therefore we can always calculate what Kb is, because Kb is going to equal Kw divided by Ka for its conjugate. And the conjugate, okay, ammonia is the base here. Its conjugate will be for the acid, ammonium. And so this is going to be the Ka for ammonium. So this is equal to 1.0 times 10 to the minus 14 divided by the Ka for ammonium. What is the Ka for ammonium? Look on the chart there, and it says 5.7 times 10 to the minus, I can't read it, 10? Thanks. It says 5.7 times 10 to the minus 10, which is equal to, this should equal 1.8 times 10 to the minus 5. That's where I got the number from. I got the number from because that's how we're going to calculate all the Kb values. All the Kb values are going to be calculated in this way unless it's given. Now, I didn't do something for amide. You know, for amide, we should have considered Kw. But I didn't bother considering Kw for amide. Why? Because I didn't bother considering it because it's not really going to change the hydroxide, and I was just looking at this. But will Kw have perturbed it? Maybe, maybe not. And so I didn't do it completely correctly for amide. But for ammonia, I'm going to do it. And so what we'll do is, let's start off with 0.100 molar. 0.100 molar is just your kind of standard molarity for these. And this is going to be minus x molar, plus x molar, plus x molar here. And then at equilibrium, I'm going to have 0.100 minus x molar, and x molar. Okay, so we're going to solve for x here. And so Kb is going to equal x squared over 0.100 minus x. Now 10 to the minus 5 is going to favor the reactant, so I'm going to just go ahead and try the simplifying assumption and see if it works. But I worry because it's not super small. But regardless, it doesn't take much time to just try it. And so SA versus debating, will it work or won't it work? You know. And so this is going to give me an x value of square root of 1.8 times 10 to the minus 6. And I get 0.0013416, let's say. All right, if I calculate my percent change, it's going to be x over the initial, which is times 100, which is going to be 1.3% change. And so it's good. It worked well enough. I mean, 1.3 is getting on the bigger side, but it's okay. And so what we're going to have here is this. We started off with 100, we lose 1.3, and so we're going to be left with 98.7. So 0.0987, or actually not 1.3, sorry, it's 134. 134 would be 1.34. It would be 98. It's 1, 6, 986. I'm just going to carry that many digits. And then over here, I'm going to get 0.0013416 molar, and the same for hydroxide, 0.0013416 molar. And so what we're going to see is we're going to see about a 1.3% hydrolysis. It's a very weak base. 1.3% reaction. Did I get that right? No, I screwed this up, didn't I? Screwed up the math. No, I guess I didn't. 0.09865, that's right. All right, so we have 1.3%. Now what we have to do is we have to ask ourselves, do you think KW will add significant hydroxide to this? The most hydroxide KW will add will be 10 to the minus 7, but it's going to be less than 10 to the minus 7 because of the common ion effect. But even if let's say we added 10 to the minus 8 additional hydroxide. If we added 10 to the minus 8, 10 to the minus 9 additional hydroxide, that's like 7 to 8 zeros. So it would be 0.0000, and then it would be adding to a digit out here. So if we went 3, 6, 7, we add to this digit. Is it going to change much? Well, let's go ahead and calculate it then. We're going to calculate this as a step 2. Now, for bases, we look for hydroxide. Did I write that? Here. For bases, we look for hydroxide producers. For acids, we look for hydronium producers. So the other hydroxide producer is going to be water here. So it'll be H2O liquid plus H2O liquid. This is going to produce hydronium and hydroxide. The common ion here is going to be hydroxide. Hydronium we're going to reset. And then what I'm going to do is I'm going to just take the hydroxide produced in step 1 and bring it down to step 2. Get this here. So I'm going to take the hydroxide produced in step 1 and bring it down to step 2. So this is the hydroxide from step 1. And then the change is, well, we're going to let the water hydrolyze. When the water hydrolyzes, I'm going to produce some hydronium and hydroxide in equal amounts. And then at equilibrium, I'm going to get X molar hydronium and then 0.0013416 plus X molar hydroxide. So I'm going to add X additional hydroxide to step 1. All right, I'm going to plug this into my KB equation. The KB is going to equal, or no, this is not KB, sorry, this is KW. I'm going to plug this into my KW, and so I'm just going to get X, the hydronium, times the hydroxide, 0.00133416 plus X. And this should equal 1.0 times 10 to the minus 14. And therefore, I'm going to use this simplifying assumption here. So if I use a simplifying assumption, this is going to be X times 0.00133416. And therefore, X is equal to, let's do that, 1 times 10 to the negative 14 divided by 0.00133416. I forgot to do something else. But this comes out to 7.453 times 10 to the negative 12. Okay, so doing the hydronium comes out to 7.453 times 10 to the negative 12. And then the hydroxide, this is going to equal 0.00133416 plus Okay, how many zeros do I need? I need 11 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 7, 4, 5, 3. Now, when I look at this, I said the max I'm going to produce is 10 to the minus 7. I produced a lot less. I produced a lot less is because we already have a lot of hydroxide in there to begin with. So did it change it much? Would you say this change is significant or negligible? That's a negligible change. And in fact, what I'm going to end up with is this, 0.0013416. I'm going to ignore that extra bit. And then let's check our K value. Here, I'm going to ignore that extra bit and see if that screwed up my K value. So let me save this before Word decides to crash on me. So K is equal to, actually I think I have this in my calculator still, yeah. All right, times 0.0013416, 0.0014316, and I get K value 1.06, not great, times 10 to the negative 14. I was expecting better, because this would round to 1.1, and it should be 1.0. But then I had a 1.3% change. See, these are all factors you have to consider. I had the 1.3% change, so that means that the simplifying assumptions, we're introducing a little error into our x value. So is this off, 1.1 versus 1.0, because of this simplifying assumption? Uh-huh.
I think you actually typed it in wrong.
Oh, did I?
Yeah, it should get like 9.9.
All right, that sounds better. Yeah, I could have typed it in wrong. What did you get then?
I got like 0.9989.
All right. And so you got 0.99, how many nines?
There's like 2 9s and then 8 9.
8, 9 times 10 to the minus 14. I'm going to move the decimal over. So if you got that, then this rounds to 1.0. Yeah, so I probably should have double checked my calculations first here, but yeah, it's off a bit. And so I guess this was the calculation error here, but this is okay. Now we have to ask ourselves, did step 2 perturb step 1? And the answer is, did step 2 perturb step 1? Not significantly. Is step 1 still in equilibrium? Well, I forgot to calculate K here. Let's make sure I didn't calculate it because I know the numbers are correct here. Just to check it, let's go ahead and check it. 0.00133416 squared. 13416 squared divided by 0.09865. Yeah, and this comes out to, well, this isn't so great either. 1.82 times 10 to the minus 5. It should be 1.8 times 10 to the minus 5. I got 1.82. So off a little bit. Maybe I should carry more digits, or maybe I shouldn't have used the simplifying assumption here. I used the simplifying assumption, which is 1.3% error. But I got it mixed up. The other one, the H2O, was a good one. But anyway, going back to this, I didn't justify the simplifying assumption here. I didn't justify it because automatically it looks good. So let me justify that here. You should justify it too. So we do the percent change. Percent change is, the change was 10 to the minus 12 over the initial. The initial is about 10 to the minus 3 times 10 squared. So that's going to be 10 to the minus 11% change. This should have worked well. I would have expected this to be right on. but I'm off a little bit, but it's all right. Because that percent change is so small. This percent change is kind of big, so I expected the answer to be a bit more in error. If I'm uncertain that, let's say it was off more, then I might use the quadratic for this, just to double check it. But the situation is this. Step 2 did not change the hydroxide significantly, so it doesn't perturb the equilibrium in step 1. So both of these Ks are simultaneously good. Versus the last problem where it did perturb it significantly. And so we're okay with stepwise. And most of the stepwise problems we're going to do in these chapters are going to be like this, where step 2 generates very little additional hydronium or hydroxide. And then we could have multiple steps here. Now, the question comes up is this. Don't I have more than this? So one of the questions comes up is, aren't there more equilibria occurring here? And what about ammonium generated in step 1? Should I do Ka for ammonium? Ka for ammonium is we have ammonium plus water yields hydronium plus ammonia. This is going to generate some additional hydronium, and should I add that additional hydronium to one of the steps? Yes? Should I do this? And the answer is no, because it would be redundant. Redundant in the sense that we already did it. Actually, I'm out of time. I'll tell you how we already did it next time. But we're not done with Chapter 17. We'll finish Chapter 17 next week. And then we'll have the official exam for 17 the following week. So we'll probably have a quiz next week, but we won't have the test next week. Do you want your